small lecture, we are going to understand the behavior of electron and hole inside the nanocrystalline semiconductor. So, as we are going to understand, we are going to formulate it. Let us go back to the 19th century and 20th century. If you look into that, from Newton's to Hygiene and Dirac, de Broglie, and people are working how to formulate in the physics, and they found that then there was a competition between the particle nature and wave nature, and de Broglie hypothesis till today we have not accepted it as a law or something, but it is still a hypothesis, but it gives a better, very good physics to understand the materials also. So he gave a theory, and due to that we could understand the behavior of the material. So we are going to apply it a simple theory and to understand what happens to the electron and hole inside the nanocrystalline semiconductor. So our topic is today we are going to understand electron and hole behavior inside the nanocrystalline semiconductor. So, as we discuss the de Broglie hypothesis, what is said, the wavelength of any particle can be written as h by mv, where h is the Planck's constant and its value is 6.62 into 10 to the power minus 34 joule second, and the mass m is the mass of the body and v is the velocity of the body. Now we are going to use this simple formula and understand the behavior of electron and hole inside the nanocrystalline semiconductor. Now let us understand what happens to the electron and hole inside the semiconductor. Inside the semiconductor, let us have a simple picture, and there is an electron. So in case of the semiconductor, and there will be lots of the lattice, nothing but the atoms, and this nearest neighbors, if you took it and I take a very simple configuration of the cubic crystal in two-dimensional, the atoms are sitting at the corner. If you look into this picture, the electron has the interaction with the atoms. So if you look to this configuration, you can easily understand that now the electron is bound at the lattice side. So if the electron is bound inside the lattice side, what happens? This electron have a effective mass inside the semiconductor. We call the effective mass. And so the electron has an effective mass inside the semiconductor, and which is always less than the rest mass of the electron, which is nothing but the m0. The rest mass of the electron m0 is, right, this is 9.1 into 10 to the power minus 31 kg. What do you mean by the rest mass? When electron is free from any interaction, that we say that it is the rest mass of the free electron. This is the mass of an free electron. But here the electron is bound inside the semiconductor, so it has a effective mass. So the velocity of the electron, again due to the bound nature of the electron and its velocity also modified, it is not exactly equal to the light velocity. Its velocity is v is less than the velocity of light into 10 to the power 8 meter per second. So now let us take a typical example of a semiconductor where the mass of the electron, effective mass of the electron is equivalent to 0.1 of the m0. Due to the bound nature, it is a typical value of the semiconductor, and the velocity is 10 to the power 5 meter per second. Similarly, the effective mass of the hole is a little high because the hole is always at the lattice side, electron is in the other side. That's why the hole effective mass is lower than the electron, and that mass is m whole star, and we write it 0.4 m naught. But the velocity of the hole is nearly equal to the electron velocity, that is meter per second. So now we have all the information. Let us find out what is the typical de Broglie wavelength for the electron and the hole inside the semiconductor. If you calculate the wavelength of the electron inside a semiconductor and you put the value 6.62, that is the Planck's constant joule per second, and divided by effective mass of the electron 0.21 into m naught is 9.1 into 10 to the power minus 31 kg, and your velocity is into 10 to the power 5 meter per second. And if you calculate it, and you get the close to 73 nanometer. Then now you calculate the de Broglie wavelength for a hole, and if I put it, so de Broglie wavelength for a hole, and what you get, and if you put the value 6.62 into 10 to the power minus 34 joule second by 0.4 into 9.1 into 10 to the power minus 31 kg into 10 to the power 5 meter per second. So what value you get? And this value is close to 18.2 nanometer. What you get? Now you think this is a semiconductor, particular semiconductor. If I reduce its size below 73 nanometer, so what will happen? The electron inside it cannot form a wave. They will confine inside the semiconductor. So we say that it is a weak confinement, because here only electrons are confined, and in the semiconductor both hole and electrons are there, still the hole's movements are there. Then when you say that this material is less than this 18.2 nanometer, we say it is a strong confinement, because in this below this length and both electron and hole are confined, basically the material becomes the fully insulated. So now in between we say it is a intermediate confinement. So how the length scale is defined? The nanocrystalline length, when length of the nanocrystalline material is less than 73 nanometer, or you can say the wavelength of the electron, de Broglie wavelength of the electron, or when this length scale is in between, L is less than 73 nanometer but greater than 18.2 nanometer, we call it is the intermediate confinement, or you can write it the de Broglie wavelength of the hole, and which is less than the length of the material and is the less than the wavelength of the electron. Then the strong confinement, it is defined as length of the material should be less than the de Broglie wavelength of the hole of particular semiconductor. So what we get in pictorial, if you put, and the length scale, if you have a material and it has a strong confinement length, and we say that the radius of length of the material is the lambda electron, but basically it is the de Broglie wavelength for the electron, and there will be a confinement length for the lambda wavelength of the hole, and we say that it is a strong confinement, and we call it is a intermediate confinement, and we say it is a region of the weak confinement near the 73 nanometer, weak confinement region. So let us take one example of the material aluminum arsenide, and in case of the aluminum arsenide, and in this material the effective mass of the electron is equal to 0.15 m naught, and effective mass of the hole is nearly equal to 0.5 m naught. So now the velocity of the electron and hole, we say that nearly equal to, for both the cases, electron or hole in both the cases is nearly equal to 10 to the 5 meter per second. Now use the simple equation of the de Broglie wavelength and calculate the lambda E, that is de Broglie wavelength for the electron in case of the aluminum arsenide, and you get a value of the nearly equal to 48.4 nanometer. Then if you calculate for the hole, and you get it nearly equal to 14.2 nanometer. So for the aluminum arsenide, the weak confinement length is near about 48, and the strong confinement length is near about 14. And from this, we conclude that if you have a semiconductor, already we know what it is, its effective mass of the electron and the effective mass of the hole. So we can calculate what will be the confinement of the electron or hole inside the material. So what it happens due to the confinement? They become the complete insulator, because electron is not free or even hole is not free, so that makes the material as a insulator.